Yeah, okay. Let's just get started. So, for who doesn't know me, I'm Tommaso Urli. I've been a researcher at the Optimization Research Group in Canberra for the past 2 months. And before that, I was PhD at University of Udine, and so this talk it will be about the last project I've been working at just after finishing my PhD in Udine. So the project is about home care scheduling, which means assisting people right at their homes. So this is about nurses visiting patients which cannot move from their places, such as elderly people or disabled people. This is becoming an alternative to traditional institutional care, such as hospitalisation or retirement homes. And it has a couple of advantages over the traditional systems. In the first place, it is cost effective because no resources aside from nurses need to be allocated to assist people. So no need to allocate rooms, no need to allocate beds, and so on. Then, from a human standpoint, it's easier to accept by the patients because they can be assisted in a familiar environment. They don't need to move around, and this is a problem which has gained a lot of attention in the past 15 years. It has been studied in operational research since the late 90s, and the reason for that is that the average population age is increasing. It has been increasing since the 50s in most Western countries, and so the result is that we have a population which is getting older, and we have about the same amount of nurses and professionals to assist them. So we need to organize how these people work in a more efficient way. Home care works in this way. So as I said, caregivers, this is the general term, travel from patient to patient, and they provide a number of services. Some of these are standard healthcare services like administration of medications, physiotherapy, and so on. More simply, many times, these kind of services deal with daily activities, like getting up in the morning, having lunch, and some of these activities also require the cooperation of multiple caregivers. The problem is a vehicle routing problem, of course, around. More specifically, the temporal nature of some of these activities make this a vehicle routing problem with time windows. I'm gonna now get through the formulation very quickly. So we work in a multi-day horizon. So we want to schedule the activities maybe for a whole week or 2 weeks. For every day in the horizon, we have a number of activities which can be different from day to day. Each activity is defined by a location, which is a geographical location, a time window in which it has to be carried out, a duration, and a number of needed caregivers to fulfill the activity. On the other end, in order to carry out the activities, we have a set of caregivers. Again, each one of them is defined by a location. So this is the starting location, but also the ending location of the caregivers. We don't make assumptions here on which kind of location it is. It might be the house of the caregiver. It might be a central office. It doesn't make a difference. For every day of the horizon, we have a working time, so a shift in which the caregiver can work. It might be the whole day. It might be just the afternoon. It might be the morning. We have a set of activities which can be executed by each caregiver. This set of activities model skills. So some caregivers are not entitled to execute maybe injections. So we have a binary relation which connects caregivers with available activities and the other way around. The goal is to design the daily routes of these caregivers for every day in the horizon. There are, so which means assigning each activity to one caregiver and fix the arrival time to this activity in a way which is actually feasible in reality. We also have to take into account that some set of activities may not be assignable completely to the available caregivers because there is often lack of personnel or some activities are just too far away and it's not possible to schedule them all. So what we want to do is to provide robust solutions which may also leave some of the activities unassigned. So the goals here is first to try to minimize the number of unscheduled activities, if possible. And once this is done, to obtain the routes which with shorter traveling times and shorter overtime work, because these are the cost components that actually matter to the company. So this is what the company pays for. The problem is made more complex by a number of site constraints. So we have a maximum number of consecutive days that caregivers can work. This number is the same for every caregiver. We have a minimum number of working hours that a caregiver must work in a day. So if the activities don't adapt to that minimal number of working hours, then the caregiver doesn't work that day. And similarly, we have a maximum number of working hours, but we allow for some overtime in this case. So, but this of course constitutes a penalty to the solution. This formulation is not made up. We work with a company from Udine which provides scheduling and timetabling solutions. And they provided to us this formulation because it was required by one customer of theirs. There is also quite a bit of related work about this problem in literature. The first work is from '97, and there have been a lot of subsequent formulations. Some of them, well, most of them differ from ours in that they have mostly, so they don't have a horizon, and they especially focus on matching one nurse with one patient. This is also very important in this field because people is dealing with human beings, and especially for elderly people, it's difficult to accept different personnel every day. However, we don't take care of this aspect in our formulation. What is interesting about this problem is that a lot of work in literature is actually about real-world healthcare systems, from Europe especially. So there are works based on the healthcare regulations in Sweden, Denmark, Austria, Germany, and so on. So it is a problem which has been studied for good reasons, and most of these works are applied in the end. I'm going now to give a quick model overview. So how we model the problem. So as we said, we're dealing with the rich vehicle routing problem. We have two classes of constraints. A class is the daily constraints, because of course routing caregivers happens on a daily perspective, but we also have horizon constraints because especially the resource allocation, so which caregivers work and when, has to take into account resources which are dealt with on a horizon perspective. So we map the problem on a complete direct graph where each activity is represented by a number of nodes. Each one each one of these nodes represents one of the caregivers that have to serve this activity. So if we have an activity with 3 needed caregivers to carry it out, we basically duplicate it 3 times. Similarly for the caregivers, we have a starting activity. This is kind of a fake activity and an ending activity. The distances are weighted proportionally to the driving distance. We have also information about the driving time. This is because some of the constraints are given on distances and some other on times. And moreover, we add a fake caregiver, which serves all the unvisited. This is needed in order to guarantee that we can have feasible solutions, even if one of the activities are unscheduled. So, of course, the length of this route, of this dummy caregiver, constitutes a penalty to the problem. So this is an example of how the activity graph without the edges looks like. We have a set S of starting nodes, we have a set T of ending nodes, and then we have a set of real nodes, which are the activities that have to be scheduled. We have time windows attached to each node. The time windows are discretized by a parameter gamma. This is because we don't need fine-grained scheduling of the activities. I mean, we don't need a specific arrival time in terms of 1 minute, 2 minutes. We can have a rough estimate of when a caregiver should arrive at a location. So this parameter was arranged with the company. This also, of course, makes the domains much smaller, so the problem easier to solve. And in a way, takes into account potential delays due to the traffic conditions and so on. So this is also a cheap way to have a slightly more robust solution. Regarding starting and ending activities, they are connected with time windows which represent the caregiver shifts. And the regular activities have time windows which are connected with their service time, which is given as an input. So some of these activities actually do not have a real time window. They can be done at whatever hour during the day. In this case, the whole day is taken as a time window. So these are the variables that define a solution. So we have, and these are given for each single day and for each activity. So we have start, which is the start time. We have successor, which is the next activity to be served after the one we are considering. So this is how the routes are built, by specifying for every activity the next activity. This is a standard formulation of eco routing. And the caregiver, which is going to take care of this activity. The caregiver, the set of caregivers, E plus, represent the caregivers, the real one plus the dummy one. We have a number of additional variables. These basically make it easier to define the model. They're not really strictly needed in order to define a solution. So these are the end time of an activity, the duration, the predecessor of the activity, and the slack time. So this last one is the waiting time before starting an activity, which means caregivers can arrive to an activity location slightly before the start of the activity. And this is one measure that we want to minimize in the final cost as well. I should mention that the duration is a variable here. This is just for modeling convenience. It actually is, of course, an input data. So we have variables for each caregiver as well, for each day. So the working time, which is the difference between the starting of the last activity and the starting of the first activity. We have overtime, which is a measure of how much more than expected each caregiver is working. And we have a binary variable is working, which basically tells for each day if the caregiver is working or not. We have variables for each day. So these are metrics which summarize what's happening in that day. We have unscheduled, which is the number of unscheduled activities. We have distance, which is the total distance traveled by overall by all the caregivers. We have a cost, which is an aggregation of various measures, such as the traveling distance, the amount of overtime work, the unscheduled activities, and the slack. So this is, we're going to see later how this cost is composed. So the nice thing about this mapping is that we can model a solution as a single Hamiltonian circuit over all the nodes. for each day. So what we do is, and this allows us to use to leverage propagators which are defined for this constraint. So as an initialization step, we connect the end activities of each caregiver with the starting activity of the next one. So this is a fixed part of the solution which is not dealt with by the solver. The rest is all free, so the solver can define the routes, but these paths are already connected. So on the horizon perspective, we can limit the number of consecutive working days by posting sequence constraints on the binary strings made up by the is working variables for every caregiver. We can define objectives by aggregating daily metrics, daily costs. And this kind of representation also suggests a natural decomposition for the problem, which will be fundamental for how our LNS approach for the solution works. So now I'm going to go very fast through the constraints of the problem. So again, these constraints can be organized in essential constraints, which have to be there to define what a feasible solution is. We then have redundant constraints, which are just meant to speed up the resolution process, but they're not fundamental. So first, we define the routes by establishing the relation between the successor and predecessor variables. This is done through element constraints. So for each activity I, we ask that the predecessor of the successor of I is I, and vice versa for the successor variables. We then link the starting and ending location, as we have seen the initialization step. We then ask that the successor and predecessor variables determine circuits on the graph. This is done by posting a single global constraint. In the framework we use to model the problem, G-code, you can also provide the traveling distance metrics, which is TD in this equation, and a forward distance array, which is an array where the distances of the selected edges are saved. This is quite nice because then it's quite easy to define the costs based on this. For each caregiver, we assign the caregiver to her starting and ending locations. We also ask that along a route, the identity of the caregiver is conserved. So if I'm in an activity A, the successors of A has the same caregiver as A, and the predecessor as well. And this is only done for the real nodes, because we don't want this relation to hold at the endpoints, so where the routes split. Here we forbid some caregiver from servicing some activities based on the binary compatibility relation. The dummy caregiver is actually allowed to visit whatever patient. It doesn't have any limitation. We then deal with unscheduled activities by counting how many of them have the dummy caregiver as their caregiver, and this is saved in this unscheduled variable. So these are all constraints, of course, and all these variables are constraint variables. So these constraints hold throughout the resolution process. We then compute the distance by making a weighted, a weighted sum of the forward distance array, and which is conditional to the caregiver not being the dummy caregiver. So we don't take into account, of course, the visits which are unscheduled, just the one which are. The time constraints are all conditional to the caregiver not being the dummy one. So if the caregiver is the dummy caregiver, then the start time, the slack, and the duration is always 0. This is why the duration is a variable and not just a number. And otherwise, if the caregiver is not a dummy one, we constrain the starting and ending of the activities to be within their given time windows. Differently from most Vico routing formulations, the time window does not restrict only the starting time, but includes the whole service time of the activity. This is slightly different from the standard. We then establish the relation between the time variables. So we ask that the end variable is the start variable plus the duration plus the slack. We set the duration and the slack for the depots, so for the starting and ending activities to be 0. And we ask that the time chain is respected along the route. So this means that if the route is not the dummy one, then we want the start of an activity to be the start of the previous activity plus the duration plus the slack plus the traveling time from the previous activity to the current activity. So this is quite standard. We then compute the working time as a difference between the starting time of the last activity of the tour and the first activity of the tour for each caregiver. And we compute maximum between 0 and the difference between the total time worked by a caregiver and the supposed total work time of the caregiver. And then we ask that if the work time, so either the work time is greater than the minimum work time for one caregiver, or the total work time is 0, so the caregiver doesn't work. This is done because we don't want solutions in which maybe we have all the caregivers working 3 hours a day. We want a solution in which 3 caregivers, half of the caregivers work all the time, all the day. This is because, of course, it is expensive to deploy a caregiver for a given day. We deal with the split activities by synchronizing them. So, of course, we want an activity which has more than one caregiver. We want the caregiver to get there and start the activity at the same time. So the number of values taken by the start time variable, the start variables of all the replicas of one activity have to be 1. So that the amount of values that can be assigned to these variables is 1. And the same holds for the duration. We don't do this for the slack because caregivers might arrive at different times at the location, but we want them to start at the same time. We also ask that if one activity has multiple caregivers, they all have to be real caregivers. We don't want an activity with 3 caregivers to be served by 2 real caregivers and a dummy one. So if one replica of the activity is assigned to the dummy, then all of them are, and vice versa. We now impose a couple of constraints on the horizon. So these are basically contractual deals between the company and the caregivers. So, well, we first bind the is working variables with the amount of work time. So if the work time is greater than 0, then it means the caregiver is working on a given day. And we consider the strings made up of the is working variables for each caregiver, and we ask that the sequence of ones of true values in this string is long at most k, where k is a parameter to the problem. We also have a number of redundant constraints. As I said, these make the search faster, but they're not fundamental. For instance, if we know a priori that the time windows for some of the activities are non-overlapping, then it would by forbidding certain assignment to the successor variables. So if activity A has a time window which ends before the time window for activity B starts, then we know that the activity B cannot be followed by activity A. This is very basic, and this can be done in a pre-processing step. We have a similar constraint which holds throughout the resolution. So as soon as we have time windows, of course, time windows can be so the service time of an activity can change throughout the resolution because of traveling distance, which are rigid, and can push the domains of the starting variables and the end variables. So if this happens, basically we enforce the same kind of constraints described above.
Did you add travel time to the normal 5 minutes? When it ends, plus the travel time to get to the next one?
Yeah. So so if a caregiver is not working on a day, then we connect her starting activity directly with the ending activity. So this is done again. This is a redundant constraint, and we have symmetry breaking constraint. So this is quite important when you have a dummy caregiver which takes care of the unassigned activities. So the risk here is to have a lot of solution equivalent, just activities. The activities of the dummy vehicle are ordered in a different way, and it doesn't make a difference. So we just impose an ordering of these activities. So each activity has as an index, and they can be ordered. It doesn't change the quality of the solution. And finally, we have a look-ahead propagator, which is a propagator we developed to get rid of a problem. So the problem was if you consider the successors of an activity, you might not notice that if you add one of those successor to your route, then you cannot feasibly get back to the final activity on time. So what we do is we have this one-step look ahead. We check which one of the successor can feasibly lead you to the final activity, and we get rid of all the other ones. So the cost is built as a linear combination of daily metrics, as we said. We have components for unscheduled activity, overtime, slack, and distance. They are all aggregated and converted to euros. So overtime and slack cost 25 euros per hour. This is about the same price that one of the caregivers paid. The distance contributes 30 cents per kilometer, which is about the cost of fuel plus vehicle maintenance. And unscheduled activities, they don't have a real cost, but we choose a quite high weight with respect to the other ones. And again, this was decided together with the company. So we have a search strategy which consists of two main components. One is is a custom branching strategy, which is used to build the routes incrementally. And then we have a large neighborhood search implemented on top of this model. So the branching strategy can be used normally for it's basically a search, so it can be used within a branching bound. And we actually did that to compare the performance of LNS. So the branching strategy goes day by day. So it starts from the first day, and it tries to build routes for that day, and then it moves on to the next day. And it works in two steps. First, we decide how many caregivers are working on a given day. This is done on a median first value selection strategy. The rationale behind this is that of course, we cannot start with 0 caregivers for a given day. Otherwise, all the activities would be unscheduled. And we don't want to use all of them because this can cause a subsequent day to not have available caregivers. So median was a good trade-off. And then we choose the identity of the working caregivers uniformly at random. The second step is building actually the routes. So what we do is for every day we choose the shortest route first, and then we decide the next activity to add to the route. And this is done according to a couple of heuristics, such as prefer regular nodes over final nodes, prefer incomplete split activities. These are the ones that are most difficult to schedule because they involve cooperation of different caregivers, activity with earliest end, and so on. So most of the times, just the first heuristic. So these are applied in order. So just the first heuristic actually matter, but it might be that you actually get to the last ones. Once all the routes have reached the final activity, the remaining ones are all assigned to the dummy caregiver in a single branching step. So this is quite efficient. We applied large neighborhood search as a algorithm of choice to find solutions, especially to large instances of the problem. So large neighborhood search is a local search meta-heuristic, which is based on the idea that if you explore a large neighborhood, then it's more likely that you find higher quality solutions. And on the other end, exploring large neighborhoods is computationally demanding. And what can happen is that many of the solutions you explore are actually infeasible. And if you're designing your neighborhoods, it's quite difficult to get the deltas right, so to implement local search efficiently. However, we can use a CP model to filter out, in particular, infeasible solutions because the constraints are in place. So if we only explore solutions in which the variable can get values from the domains, then the essential constraint help you in getting just feasible solutions. And we can filter out bad solution by imposing constraints on the cost. Another thing that is quite interesting is that this approach is transparent on the model. So you can have a general model of vehicle routing, and you can have side constraints. And for local search, for large neighborhood search, it doesn't matter. It assumes the model is a black box. So how does it work? Well, we start with an initial complete solution. This is obtained with the brancher we have seen, with the branching strategy we have seen. Then we proceed by alternating two steps. The destroy step, which relaxes a fraction of the solution. Which basically means we set the domains of some of the variables to the original domains. This can be done as a black box. We can relax random variables. The problem is most of the time this is not very efficient. So if you have knowledge of the problem, a good idea is to define your own destroy step, which maybe gets rid of conflicting parts of the solution. Then we do a repair step. So we re-optimize the subproblem represented by the relaxed solution. So we basically have the initial problem, but part of it is already assigned. So it's actually a subproblem. It is much smaller and easier to optimize. And this can be done again with research. So you can use the CP model to obtain an initial solution with branch and bound, and then you can use the same model as a sub. You can use the tree search based on that model as a subroutine of your search. In particular, our destroy step relaxes entire days. So we start by relaxing. So at the beginning of the search, we relax a single day, and we optimize, and then we relax another one, and we optimize, and so on. So if we get through a number of iterations without any improvement of the solution, then we increase the number of days that we relax. So now we don't relax one day anymore, we relax two. And of course, as the iteration go on, these 2 days will be different days. Exactly as before, the day could be a different day every time. And again, and you can go on until you reach the size of the horizon. Then you are basically optimizing the complete solution. And so this is basically a restart. Okay. The repair step is done through the branch and bound with the same branching strategy we used before. The only different thing is that we now have an incumbent solution. So we have the best solution we have ever found so far, so we can constrain the cost to be smaller or equal to that one. We do allow equal cost solution because it might be in many combinatorial optimization problems we have a plateau in the cost landscape, and by allowing equal quality solution, we can escape this plateau. Also, we don't solve the sub-problem to optimality. We give it a timeout, and the timeout is proportional to the number of relaxed variables. So this is in fact most often called adaptive large neighborhood search, because the amount of things that you relax changes throughout the optimization. So in particular, we give about 10 milliseconds for each free variable. We have carried out an experimental analysis. So we compare branch and bound with LNS. We modeled the problem in G-code, and this is available. The model is available if you're interested into it. Similarly, we encoded the LNS as a G-code meta engine, which is generic, so you can use it on every model. You can use it as a black box, or you can customize some of the hook methods. So, and this again is freely available. These are the things that you can customize in the G-code LNS engine. So you can change how the branching for the initial solution is done, the branching strategy for the initial solution is done. You can customize how the branching for the repair is done. You can define your own relax step, and these are a couple of methods that you need to implement. So the total number of relaxable variables is used when you use the engine as a black box. You can define a method which tells if your solution has improved. This allows to use the engine both on minimization and maximization problems. And then you have a very generic method which is executed just before the repair step. So this is typically used to constrain the solution, but everything can go in there. So we actually generated the instances because at the time at the stage of the project we didn't have any available real-world data. We tried to keep the instances realistic. So actually also the instant generator is available, and it has a number of parameters which can be used to generate different families of instances. In particular, we generated a pool of 540 instances, organized in 18 different families depending on the parameter setting of the generator. We fixed the maximum number of consecutive working days as on -1. So every caregiver has to have at least one leave day. And we automatically tune the parameters of LNS. So there are a few parameters. One is, for instance, how long do you allow the repair steps to run, and plus it supports simulated annealing style acceptance criterion for new solutions. So there are a few parameters that can be chosen. And so I will not show you tables of data, but I'm just going to summarize the results. So LNS was outperforming pure branch and bound in 17 out of 18 instance families, at least on the timeout that we used, which is 10 minutes. And it generally obtained better results for regarding unassigned activities, slack time, and overall the cost was about 40% less than the one obtained by branch and bound, which is not actually surprising, because branch and bound has to follow a very strict branching strategy, while and this can be a problem if you have a very long horizon, because the first day is basically set at the beginning of the search. Okay, at the beginning of the search, and then you basically keep optimizing the last days, how the branching is done day by day. So what happens is that, especially on short run times like 10 minutes, the first day is not routed very nicely, and this can be undone by the LNS approach. So actually, branch and bound obtain better result regarding traveling distances, but this happened by leaving quite a bit of activities unscheduled. So this doesn't help in reality, and yeah. So if you want to see the results and actually more precise description of the model, there is a paper about that from earlier this year, and yeah, that's about it. Thanks for listening. Yeah.
In your symmetry break constraints,
Mm-hmm.
you have an index to sort of impose an order in units.
Yeah. Yeah.
How does that play around with different travel?
Can you repeat the question?
Okay. Do you want this one, maybe?
Yeah, can you repeat the question? We can't hear you. Thanks.
The symmetry breaking constraint where Tommaso adds an index to the activities to impose an ordering when an ordering doesn't matter. But the question was, well, if you have travel distances or travel times between activities, how I can imagine where you may order things around, and then I don't know, the distance will be, you're further away because you're ending at A, or you're further away because you're ending at C, and that may have an impact.
Yeah, sure. So the thing is, the symmetry breaking only works for the dummy vehicle, and time constraints on the time constraints and distance constraints are conditional to the caregiver not being the dummy one. So this is why the duration is 0, and it can be a variable, which can be the real duration or 0, because if we assign an activity to the caregiver, then all the traveling times and traveling distance are like shrinked to 0, and this is just a modeling choice. So in this perspective, it doesn't really matter the traveling distance. You can safely order the activities of the dummy caregiver. Any other question, you guys?
Yes, I have a question here.
Okay.
Can you hear me?
Yeah.
Could you please go to the slide where you define the working time and the overtime? I think was around 30 something.
Okay.
Yes. The next. Yeah. So actually, here I was a little bit confused why you define working time as a start time of the last activity minus the start time of the first one, because you, as a caregiver, you may go to your last patient for that particular day, let's say at 8 o'clock in the evening, but you may finish your work at 9 or 10, and this simply means that you will be working more time, and afterwards, if you go to slide 40, I think, you can see that one working hour costs for 40, 39, yes, one working hour costs 25 euros per hour. So actually, the caregivers would be unsatisfied of not being paid for that additional time.
Yeah. So the thing is, maybe I didn't explain very well. But when I mean the first activity and the last activity, I refer to the fake activities that we have for each caregiver.
Okay.
So these are like the starting location. It might be the caregiver's home, and again, the ending location might be the caregiver's home. So we don't take into account these ones. These are just used to compute what is the time the caregiver stays away from work or from home or the office during a route.
So actually here the first variable start is referring to the...
So it's very small, but it's start TED, which means the final activity of employee E in the ID, and minus start SED, which means the starting activity of employee E in the ID.
So the last activity is when the caregiver goes home, or?
Yeah.
Okay. Thank you.
Yeah, Patrick?
So you mentioned that you don't give better solutions.
Yeah.
So because you want to be able to shift to an equivalent solution on
Yeah.
one day, which will then allow you presumably to get a better solution on another day.
Yeah.
So I'm just wondering if you compared that with actually imposing a strictly better constraint.
Yeah.
And just sort of hoping that, well, eventually you will look at
Find one.
2 days and find a better solution.
Yeah.
By adjusting both of them simultaneously.
Yeah, we of course we tried both approaches. So when I say that we tuned the parameters,
Yes.
So in Udine we tend to have this approach. We expose all the algorithm variants, so which means acceptance criterion, numeric parameters, and so on. And then we basically optimize everything. So these result and this optimization of the parameters is done with statistical significance. So this means that this way was much better than all the other ways, and which might be a poor explanation. But the thing is, since our search is timed, maybe this is not so important to have to. So if you have time to do that, and you can, you will find it almost equivalently if you impose or not the constraints.
Basically, this means that by randomly picking equivalent solutions to small subproblems, and you get better results than the time it will take you to actually find the better solution.
Yeah, and it is not guaranteed that you will find one. So this just works better on the practical point of view. Yeah.
So Bloomfield has been using a similar framework to solve these problems on HVAC controlled scheduling heating, so as to minimize the energy consumption in a building. And so she's got this LNS and big over there.
Okay.
And she's also been using auto tuner.
Okay. Which one?
She used SMAC, and I was wondering whether this is the work by Frankfurter, the latest work by Frankfurter, Holger Kuss.
Yeah. Okay.
And so I was just wondering whether you got any idea of SMAC versus FRACE.
I haven't used SMAC. I know Holger Ross is quite on this kind of approach, like exposing all the parameters and then optimizing them. We use a tool called JSON to run, which is used to design a set of experiments, and then once you have designed a set of experiments, you can either run them as a batch or optimize the configurations. And this tool is based on FRACE, other automatic tuning approach. We have been using it for a while, and we're quite happy about that. And the reason of FRACE. So FRACE has this idea that you have a fixed number of configurations, and you run each one of them on a set of instances. And once you have exhausted that set, you rank the results, and you the configuration which are significantly inferior. So it's a race in this sense. So you get a smaller set of configuration, and then you run this subset of configuration on more instances, and you keep doing this.
And do you end up with one final configuration, or one that depends on
it's difficult to say. So it might be that, of course, you have. So you end up with a. So the invariant is that you end up with a set of configuration which are not significantly different. They might be different. So what can happen is that if a parameter is not really significant to the performance of the algorithm, it doesn't get pruned. And yeah, so if you're very lucky, you end up with one single solution, one single configuration. But in many cases, this is not the case. Yeah. Yeah. Altogether. So we have. No, it's overall tuning. So you will get a set of configuration which on that specific data set are comparable. It is usually not very useful. So this is something we try to avoid.
What we mean is define features of the instances, and
okay.
what you learn is the function of features parameters.
Yeah, so we actually tried to do that with trying to learn of the instances and the results. Well, and the results given some parameters of the algorithm. If we could find a way to predict the best parameters of the algorithm from the set of features, we have some minor results on that on a scheduling problem. So if you want, we have a paper on that, a recent paper on that. So we have been working with the statistician to do this, and it's quite an interesting approach because this kind of tuning is what we call fixed parameter tuning. So you end up and you hope that these will perform well on unseen instances. We think that if we use the feature of one instance to predict the ideal parameters, this has better generalization performance. But this was fixed. Any other questions?
None from us. All right, thanks, Tommaso, one more time. Thanks a lot. And then we'll have the next seminar will be on September 26th, and it's going to be an outside speaker, Tanya Laddie, who's a Weiss Society and Science Research Fellow, will be giving a talk. I'm not exactly sure what it's about, but I should have an abstract in the next day or so. And if anybody wants to talk in October, please send me an email.